Hello, everyone, and welcome to Distributed Model Training Workshop on AWS EKS. My name is Alex Jankulski. I'm a Principal Solutions Architect in the ML Frameworks team at AWS, and I specialize in orchestration of machine learning workloads on AWS using containers.
Hi, everyone. I'm Shubha Kambatkone. I'm a specialist in the Frameworks team focused on helping customers build their ML models on EC2 and open source tools and technologies.
Yeah, hi, everyone. My name is Imran Yunus, and I'm a Principal Solutions Architect at ML Frameworks team, and I focus on distributed machine learning and deep learning kind of problems.
In today's workshop, we will follow a simple workflow. First, we'll set up our development environment using Cloud9 on AWS. Then we'll create an EKS cluster. We'll create a shared volume where we'll store the data later. We will build a deep learning container that has our distributed training code. We'll execute a job to download the training data and store it on the shared volume. Then we will run distributed model training using PyTorch and Torch Elastic. And finally, we'll run a test to see how good of a model we have built. In the workshop, we will use the following resources. The event box link provided at the top will let the participants provision a temporary AWS account where they can complete all of the steps in the workshop. We will use a GitHub open source repository on the second link, which will allow everyone to follow through the workshop steps and copy and paste code from the repository into their development environment to complete all of the steps in the process. First, let's log on to the AWS console and set up our IDE. I will be switching screens between this presentation, which describes our steps, and my demo screen here, as well as the open source repository full view. So to start off, I will go to the demo launch page, which can be accessed through the short link bit.ly/distributed training workshop -EKS event. This will provide a launch button for us. And let me make the font bigger here. When you click the launch button, you will be provisioned and assigned a temporary AWS account. You'll have to agree to the terms and conditions for the workshop. And on the next screen, you'll have a chance to enter your email address so that you can be sent a temporary password to log on to the AWS console. While I'm waiting for the passcode to arrive in my mail, let me scroll to the distributed model training workshop repository and describe briefly the setup that we're going to use in today's lab. So we'll execute everything inside your browser. We're not going to need to. All of the steps will run on the cloud. We're going to work inside the Cloud9 IDE, which is a full development environment running on EC2 instances in AWS. And from here, we will clone the GitHub repository and execute all of the scripts for all the steps in the workshop. They'll create infrastructure inside of VPC, Kubernetes, or managed EKS cluster with one node group where our workloads will run. And we will build the container here, push it to the Elastic Container Registry, and then we will instruct EKS to run that container in several different configurations to do the distributed training. The nodes in the cluster will pull the container from the container registry and run the job here, while the data is being stored in an Elastic file system, which is mounted and shared to all of the nodes and pods in the cluster. So I have now received my temporary password code, and I'll paste it here to gain access to my console. Once you're authenticated, you will be presented with the team dashboard screen. If you click the AWS console button, you will also see temporary credentials on the screen. It is important to copy those and save them locally on in a temporary file, because we will need to refer to these credentials later in the workshop. Once you've copied the credentials, click the console button, and that will log you in to the AWS console and provide access to your temporary account. As I mentioned, we are going to use the Cloud9 IDE, which has already been set up in your account. So we will just type Cloud9 and open the Cloud9 service. An IDE called Workshop is already provisioned in the account. So I'll just click the Open IDE button, and this will bring us to our environment where we will run all of the steps from the workshop. The Cloud9 IDE is, as I mentioned, fully functional development environment, which runs on AWS EC2. When not in use, it will actually stop the EC2 instance, so you're not accumulating any charges. And the first time you want to use it after a period of inactivity, if the instance is shut down, it will automatically start up and resume the state that you had when you last were active on the environment. So I'll use two screens here just so I can show the steps better. However, in your workshop, it is sufficient to just use one of the screens. I'm pasting the credentials that are saved from the earlier screen in both of my terminal windows here. But I will use just the bottom window for the time being to create the EKS cluster. So the first, this workshop can be completed in your own AWS account as well. And if you wanted to do that instead of using a temporary account provided by AWS, then you could follow the instructions in the setup document in the prerequisite section. So this document walks you through setting up your own Cloud9 ID and giving permissions to your AWS account and configuring the Cloud9 ID so that it can execute all of the steps in the workshop. And as a last step, it shows how to clone the open source repository that we'll be using today. So to clone the repository, you could also just copy the clone link from the repository itself and execute git clone, which provides a local copy of source code. The repository is structured in the various steps. We'll go through step 1 through 6 here, and each of the steps is executed in its own directory. First, we will go into the step to create an EKS cluster. For that, we switch the working directory to 1 create cluster, and we'll execute the scripts provided in this directory in order. First, we'll provide credentials to the local Cloud9 terminal by pasting the AWS access key ID and AWS secret access key that we have saved. We use US West 2 as a region, and output format we are going to use is JSON. As soon as we complete this configuration, the Cloud9 ID asks us a couple of questions. So the first one, we would say cancel, do not use managed temporary credentials, and then permanently disable to basically opt for using the credentials that we just entered from the IDE for the workshop. The second step would help us install some tools in this environment, like EKSCTL, kubectl, and kubectx, which will help us throughout the workshop to provision the infrastructure and to interact with our Kubernetes cluster so that we can run distributed model training on it. And in order for these changes to take effect in your shell, it is not required, but helpful to execute this command. Source home folder.bash rc. This basically creates some aliases in your environment that you can use as shortcuts. Instead of typing kubectl later, you'll be able to just type K to do the same thing. I'll source that bash resource file in my other shell as well, so I can access the shortcuts from either window. And now we're ready to run the script create cluster which will actually start the process of creating a Kubernetes cluster. Just to explain a little bit about Kubernetes, a Kubernetes cluster is a group of virtual machines running on any given infrastructure. It could be running on premises, around VPC, or as a managed service on AWS. The Elastic Kubernetes service is basically the open source Kubernetes distribution, which runs on AWS in a managed way, which means that AWS takes responsibility for provisioning and managing the cluster, while you are able to have full control of the jobs and workloads that are executed on the cluster itself. When you're using EKS, the master node that contains the API server runs on AWS-owned infrastructure, and the nodes of the cluster, which are the node group we're going to use today, run in your own VPC. So you're able to see the nodes where your pods will run, but you are not able to have shell access into the API server, which is managed for you by the Elastic Kubernetes service. So to create the cluster, we basically use this cluster manifest, which says that we're going to create a cluster called do EKS of this version in this region. We're going to use 2 availability zones and integrate it with IAM through OpenID Connect. And we'll have 1 managed group called workshop node, which is of type C5 4x large, and nodes from this node group will be distributed between these 2 availability zones for high availability. The EKS-CTL command is what actually kicks off creating the cluster. It uses this manifest that we just reviewed, and this is the command. With 1 command, you basically kick off the cluster creation. What this does in the background is generate CloudFormation scripts for you and provision all of the infrastructure necessary in order to get your cluster up and running. I will quickly show the CloudFormation tasks that are going on in the background. This is for informational purposes only. We can see that there's this do EKS cluster stack that is being created, and there are several events that are in progress. So with this, while the cluster is being created and we're waiting for it to become ready, let's pass the microphone to my colleague Shubha Kumbadakoni to give us an overview of AWS's ML capabilities and the reasons why we want to do distributed model training on AWS.
Hello, everyone. Thanks, Alex. Hello, everyone, and welcome to the workshop on distributed training using EKS. As you wait for the clusters to be set up, I wanted to take some time today to kind of talk about why we are seeing distributed training becoming increasingly relevant, and what are some of the challenges that you need to be considering from an infrastructure perspective as you set up your distributed training architectures. What we've seen in the AI/ML landscape is that models are increasingly becoming larger and more complex. And there are a couple of reasons why that's happening. Right? More customers are adopting deep learning because the amount of data that they need to analyze is increasing. It's becoming pretty large. They're generating terabytes of data on a daily basis, and they want to be able to train their models on these large amounts of data. So they're increasingly adopting deep learning, which relies on neural networks as well as transformer-based models. And these models are fairly large. And by large, we mean they have a large number of parameters in the order of millions and much, much more. And if you look at how the sizes of these models are increasing year over year, you see that there is an exponential increase in the complexity. If you think about a BERT large in 2018 to a GPT-3, which has 175 billion parameters, to now models that are even a trillion parameters large, the size of models is increasing exponentially. But the underlying compute that is required for training these models is not really growing at 10x speeds. So that introduces a challenge of how do you then train these models in a time that is not prohibitively too large? How do you make sure that your training now doesn't take months and years? And how do you effectively accelerate your training? That is where distributed training really comes into the picture and is important. And what do we mean by distributed training? It's really the term that is used when a single training task is no longer relegated to just a single GPU or a single server, but instead is spread across multiple GPUs. And how you architect it is what we're essentially covering in our workshop series. There are a couple of challenges that are inherent to distributed training. You need hyperscale compute. You need to be able to easily deploy large clusters, sometimes at HPC scales, for training these large models. And the cloud, if you think about it, is ideal for that kind of hyperscale compute because you can get compute on demand and you don't have to spend months setting up your on-premises infrastructure for doing these training jobs. Training is also done typically on a large number of multi-GPU nodes, so you need more powerful servers that can deliver the performance that you need. The nodes also need to work in a parallel fashion or a distributed fashion to complete the training job. So there is high-speed inter-node communication that becomes necessary, as well as GPU to GPU communication needs to be pretty fast. Data has to be shared across all the nodes, so there needs to be a distributed file system that needs to be present. And as you now think about scaling your training across multiple nodes, fault tolerance becomes important. So your training job needs to be resumable. If you get interrupted, you need to be able to pick up from where you left and not lose all of the work that has been done. If you think about distributed training, there are certain constructs that are in place today. Data parallelism is an intuitive way in which all of the nodes have the model, but they work on a subset of the data, of the training data. And then there's model parallelism, where the model is sharded across all of the nodes, but every node or every server works on all of the training data set. And in model parallelism, we do have pipeline parallelism and tensor parallelism. And each of these have their own advantages, and they come with their own challenges as well. So let's talk about data parallelism. So like I said, this is a fairly intuitive distributed training construct. In this, each of the worker nodes can store the entire model in their memory, and the model works on a subset of the training data, which is known as a mini batch. So what happens is every worker node trains on a subset of the data. And once the model has converged on that subset, which is called a mini batch, the new model parameters, or what we call the gradients, are communicated across all of the worker nodes, so that at the end of that communication phase, all the worker nodes in your cluster have the updated model parameters. Now, once this is done, the next batch of training data is sharded across all the four or all the worker nodes in your cluster, and the process repeats till we reach the required accuracy, until the model converges. So that is data parallelism. But model parallelism is when the model is sharded across all of the nodes in your cluster. And this can happen because the model is too large to fit into the memory of a single node anymore. So in that case, you need to look at ways in which you can shard the model across all of the workers and then train it on the entire data set that is available. For instance, in the pipeline parallelism, what happens is that every layer of your model is assigned to a specific worker. So we form a pipeline of execution. In this particular example, we see that layers 1 and 2 are assigned to worker 0. Layer 3 is assigned to worker 1, and layer 4 is assigned to worker node 2. So that becomes your pipeline of execution. Each worker node will execute or will train on the entire training data set. While pipeline parallelism is a good way to address the problem when the model becomes really large to fit onto a single node, the pipeline parallelism has an inherent challenge where one particular node or one particular stage of the pipeline can become a blocker for the execution, because it is much slower than the remaining stages. Tensor parallelism is we can also call it intra-layer model parallelism. So this is another approach of a model parallelism where each worker node has every layer of the model. That way you're kind of overcoming the inherent challenge of pipeline parallelism. But what tensor parallelism requires is a high degree of synchronization between all of the workers, and ensuring that all of the updated model gradients and parameters are in lockstep across all of the nodes in your cluster. Now, AWS has the broadest and most complete set of machine learning services that can help meet you wherever you are, based on the kind of flexibility and the kind of control that you want over your machine learning applications. If customers want to do API calls, and that's the kind of flexibility and that's the kind of low lift they want, we do have AI services like Recognition, Poly, and Comprehend that can provide that. If you want to build, train, and deploy your models, but you want to offload the infrastructure selection, the CI/CD process of maintaining your model, then Amazon SageMaker is a really powerful tool to help enable that. And we, in fact, have a workshop next week where we go over how to do distributed training using Amazon SageMaker and the DDP libraries there. But if you want to have a high level of autonomy with the tools that you use, with the infrastructure options that you use, with the open source technologies that you want to use, then we do have powerful infrastructure services, a wide range of orchestration tools and software that you can leverage to build your distributed training as well as inference architectures. Double clicking on that point, we have a pretty broad range of high performance accelerated compute instances that range from A100 powered instances like P4D, G5, which has the A10G GPUs, DL1, which has the Intel Habana Gaudi accelerators, and Trainium, which is powered by AWS Silicon, and TRN1 instances that are currently in preview are powered by Trainium, and it's set up for distributed training with high-speed networking and powerful accelerators. So we have a choice of compute instances that you can choose based upon your price, that is the cost, as well as the performance that you need for your training jobs. We do have storage services like EFS, FSX for Lustre, S3, and EFA, which provides high-speed networking. It's a networking service called Elastic Fabric Adapter that supports up to 400 Gbps of high-speed networking. We, of course, have orchestration services that can both be managed, like EKS and ECS, as well as open source software that you can leverage, like Kubeflow, Airflow, and build your architectures on AWS. I wanted to close by talking about our customer, AI21 Labs, who is a startup that's based out of Israel that has a product called WordTune that is a writing assistant. And they basically use an NLP model. They use a Jurassic 1 jumbo model, which has 178 billion parameters. And we helped them build out their distributed training architecture on P4D ultra clusters using the high-speed networking of EFA. And they were able to deploy their distributed training architecture and train their model on AWS much more faster and scale much more easily when compared to doing this on premises. So the cloud or AWS with hyperscale compute readily available, powerful infrastructure services readily available, can really accelerate the time to deploy the training architectures, as well as meet the time to train requirements that you may have. With that, I want to hand it over to Imran to go over the code specifics of what we're doing today.
Thank you, Shubha. So now I'm going to basically explain what task we're going to run on our EKS cluster. So we are going to train a deep learning model on an image data. The data set that we are using is a CIFAR-10 data set. It's publicly available. It consists of 6,000 images, which are categorized in 10 classes. And each image is 32 by 32 pixels. And we're going to train a deep convolutional neural network. The code is provided in the workshop. The convolutional neural network has 6 convolution layers divided in 3 groups. Each group has 2 convolution layers, followed by a max pooling layer and a batch norm layer. The network ends in a linear layer, and then at the end, I have a final layer output layer with the 10 outputs, because I have 10 classes in the network. The model is wrapped in a class, which I just call my CNN class. So in the training script, which is also provided in your lab, we have the very traditional PyTorch model training code with 2 differences, and there are other minor differences I'll show also. The main thing is that we are importing a data distributed parallel class, and we're also loading a elastic distributed sampler. So I will show you how these are used. In the top, I have some parameters that we can set in the YAML file when we launch the job. For example, the batch norm, the batch size, learning rate, etc., etc. The next thing is the data loader. So whenever you train a PyTorch model, you have to first define a data loader. In our case, we are using the Cypher10 data. And the Cypher10 data, when you download it, it has a tar.gz file. When you untar it, what you get is a bunch of pickle files. Each pickle file has basically data stored in lists of arrays, NumPy arrays. They are not stored as images. So when I unpickle with this small utility, which is also provided in the lab, what I get back is the images list of arrays and the label, which is also NumPy array. So before moving forward, we have to convert these NumPy arrays into a tensor data set, which is a PyTorch class. So this is what the get tensor data set utility does. Again, it's also in the code. And then I have to create my data loader. For this specific work, we have to basically provide a data sampler to the data loader, and that is going to be elastic distributed data sampler, which is very specific to the training on EKS clusters. Once I have my data loader, then I have to create my model. So the model, as I mentioned earlier, is my CNN class. So I'm creating my model, but I have to then wrap it into a distributed data parallel class. And that's all you need to do when you're distributing model across multiple GPUs. So distributed data parallel basically takes care of copying the model on every GPU available. The rest of the stuff is pretty standard PyTorch. I have to create my loss function, and I have to create my optimizer. Then in the main function, I have to start from defining which backend we are going to use for gradient averaging. And because we are running on CPU, we're going to use the glue backend. If you're running on GPUs, you have to use NACL backend. The other thing I need to get is the rank, because in EKS, when you create a cluster, every pod in this training loop will have a rank assigned to it, which is unique integer ID. And you want to get that because that is also used to define which pod is going to save your data or last model. And then I'm basically just calling these functions that I defined earlier, getting my train data loader, and I'm initializing my model. I also want to save and load the checkpoints. So this function here will see if there's a checkpoint already stored, and it will load that checkpoint and start from that. If no checkpoint is there, it will start from the very beginning. This is needed if your training gets interrupted, then you basically have to go back and run them again, and then it will start from the previously stored checkpoint. Finally, I have the main training loop. And as you can see, it's basically pretty standard PyTorch training loop. There's not much difference here. So I'm basically looping over all the epochs, and then I'm looping over my data loader. It returns me a batch of input and labels. I'm doing a forward pass. I'm calculating my loss. I'm doing a backward pass, and I'm stepping forward. And finally, I'm just writing down some parameters like the loss, basically, for every iteration, just to see how it is progressing. One thing that is different is that storing the checkpoint. So for each epoch, I'm storing my checkpoint, and the checkpoint basically stores the model weights at that time and what epoch is there and the optimizer state. And I'm storing it only on one pod. If you are running multiple pods, you don't want to write the model from every pod. You only want to write the model from one pod. And that's why I'm using the rank. Once all the epochs are done, we're going to store the final model. And that's it. So that's the whole code for model training. Once the model training is finished, we're going to basically run the test code to see what is the final accuracy. For that, I have another script here. Again, pretty standard PyTorch. This script will not use torch elastic. This will run only on one pod because we are just doing a forward pass to the model. So I'm only going to load the data loader. Again, I'm loading the CFA test data now, which has only one pickle file. And I have to convert into a tensor data set because I get the NumPy arrays back from the pickle file. And then I have to create a data loader. This time, I'm not providing any data sampler. So it's going to run on a single node, just like a single machine. And the main function starts from the calling this function, which gets the data loader, and then I'm loading the model from the stored model. And finally, I just have to basically do a forward pass on this model using the test data. And I'm going to calculate some of the metrics. And that's it. That's the whole code. I do want to point out that in all these cases, all the data is being read from a common disk, which is mounted on every node. So whenever I say that I'm saving a model and loading a model, this is happening on a common disk that is mounted to every node. With that, I think I'm going to basically return to Alex to continue.
Thank you, Imran. And now let's go back to our development environment. By now, the cluster has completed creating. As we can see, the script is done creating the cluster, and the local environment was updated with the new cluster context, which is saved in the local kube config. And we also were able to execute a command to see the available nodes in the cluster, which are displayed here. So from this point, I am going to split my screen in two here. If I execute the command to get the nodes, I can do that at the same time at the top of the screen. I will watch the all of the pods that are running in the cluster here so that we can keep an eye on what's going on. So a little spelling mistake here. So as we can see, nothing is really deployed in the cluster yet, since we just created it. What we're going to do is execute script 1.4 to deploy packages, and this deploys the Kubernetes metrics server, the Torch Elastic job controller, and the etcd server to the cluster. The metrics server we use to monitor node utilization during the training jobs. The Elastic job controller is what contains the custom resource definition for Elastic jobs, which we use for distributed training. And the etcd instance is a coordinator for the workers in the distributed training job, which allow them to coordinate the work between themselves. So this completes the server, the cluster setup portion of the workshop. Next, we're going to create a shared volume which can be mounted in each of the pods that we're going to run in the cluster. I'll scroll here to remind us that we are now at step 2 to create a shared volume. To do that, we will change our current directory to the create volume step, and we have 2 scripts to execute here. First, we will use the AWS CLI to provision an EFS volume in the region that we have configured and in our current VPC. So this creates the EFS volume. We can go to the console, type EFS, and we'll be able to see that volume created in our account. And in order for this volume to be able to be mounted by each of the nodes in each of the availability zones, for each subnet that belongs to these availability zones, we're going to create a mount target. And these are the 2 mount targets that got created, one for the US West 2A zone and one for US West 2B. The next step is to actually provide the information about this newly created EFS file system to Kubernetes by configuring a persistent volume and a persistent volume claim. And Kubernetes is able to do that through the use of a container storage interface driver for EFS. So this second script will deploy the CSI driver to Kubernetes. You will see the CSI controller and nodes running in the cluster. Then it creates a persistent volume, a storage class called EFS storage class, a persistent volume called EFS PV, and persistent volume claim called EFS PVC, which will enable us to mount this shared file system into any of the pods. When all of the containers enter the running state, we will see that this persistent volume claim will become bound to the volume and available to all of the pods. So if I get the currently available PVC, we now see that the PVC is bound and ready for us to use. Next, we will just use our Cloud9 IDE to build a deep learning container and push that to the Elastic Container Registry. For that, I'll just need this one screen, and we'll execute step number 3. There are just 2 simple scripts here. 3.1 will build the container, and while it is running the Docker build, let me walk through what the actual build is doing. It's using this Docker file, which takes the base image of Ubuntu 20.04, installs PyTorch in this container image, and then just copies all of the code that Imran walked through earlier into the container image, as well as a bash script called data prep, which we're going to use to download the data from the web. And we are at step 4 out of 10 in the building of the container. Basically, we're installing PyTorch and various dependent packages. And then the rest of the steps are pretty quick. And our container is, the container image is done building. So in order to use this image from the cluster, we need to share it with all of our nodes in the cluster. And that is done by pushing the image to the Elastic Container Registry in the account. So this is what we're doing with the second script in this step. We can also see the Elastic Container Registry by typing ECR in the console. I clicked on EKS, so this shows us the cluster, and ECR will show us the container registry, and this is the container that we just pushed into ECR. So as a next step, we are going to run a pod that will use this image we just pushed and run it on one of the nodes and execute the data prep script, which does nothing but wget the CIFAR dataset and store it in the shared EFS volume. To do that, we will cd to step number 4, and I will launch the pod by executing the first script. You'll see this EFS data prep pod being created. If we take a look at the status, it is container creating, but that is because now the image is being pulled from our container registry down to one of the nodes in the cluster so that it can get executed. So now that it is in status running, we can see that the container was created and started successfully. And it doesn't take a very long time. The images now, the images data set has been downloaded and the container has completed its work. If we take a look at the log files that it printed out, we'll basically see that it successfully downloaded the data set and saved it in this file in the shared volume. So now that we have the data, we've set up the shared volume, and we have the Elastic Kubernetes Elastic Job Controller in Kubernetes, we are ready to run our distributed model training job, which is what we'll do in this step. We'll see that the job will create a worker pod in each of the nodes, and these worker pods will work together to complete the training. So for this part of the workshop, I'm only going to focus on the default namespace where the distributed training will be running, so that we can better see the output of our jobs. So this step will be executed in folder 5, and as a first script, we will generate the Elastic Job Manifest. An Elastic Job Manifest is basically a custom resource in Kubernetes that's of type Elastic Job. Here we're giving it a name of CIFAR 10 train, and we're configuring it to use the etcd service that we've deployed locally in the cluster for coordination of the workers. And we're defining the job so that we would start with 2 workers, and we'll run those on C5-4X large instances and use the image that we pushed to our Elastic Container Registry. The command that we're running in each of those images is PyTorch run and the model training Python script that Imran walked through earlier. We're going to run the training for 10 epochs, and we will save the model file in this location while accessing the shared data in the EFS shared volume. The shared volume is mounted using our persistent volume claim called EFS PVC, and it is mounted in this path as we have specified here. So running the job actually applies this manifest, and as you can see, that creates 2 workers, 1 per each node. And since we ran the download job, which used the same container, the image is already pulled onto one of the nodes, so it becomes running immediately. However, the second node still needs to pull the image from the container registry. So we'll just wait for that to happen. And now it begins running. At this point, we can take a look at the logs that these 2 worker pods are putting out. And I'm using a tool called kubetail here, which aggregates the logs from each of those pods and prints them on the same screen color-coded. So you can see now that both pods, worker 0 and worker 1, are in fact doing the distributed training together and printing out the loss of the training on the screen. So you will see 2 numbers here between the brackets. The first number is the number of the epoch, and the second number is the number of the iteration inside of the epoch. If we were running this job on a single worker, there would be 400 iterations. However, because we're splitting the work between 2 pods, each of the pods needs to do 200 iterations in an epoch, and that way we're doing the work twice as fast. Essentially, the epoch goes up to 200, and then a checkpoint is saved, and we continue with the next epoch. A good way to demonstrate the elasticity of this distributed training job is to demonstrate what happens if, let's say, we're using spot instances in our cluster, or if something goes wrong with the infrastructure and the nodes get terminated mistakenly, then the job will completely recover by restarting the pods and continuing the training from the latest saved checkpoint. I'll demonstrate this by deleting the current worker pods and letting Kubernetes recover the training job. So the kubectl delete pod, and I'll just paste worker 0 and worker 1 here. So what happens now is these pods get terminated, but we still have the elastic job telling Kubernetes that we want to have 2 workers running. So Kubernetes automatically creates new worker pods. And if we take a look at the logs, we see that there is a new rendezvous happening between the two pods. They're coordinating the work between themselves using the etcd endpoint, and they find the latest checkpoint that was saved, and training continues from the latest saved epoch, which happened to be number 5. So we're now continuing to work on epoch number 6. One other detail that I wanted to mention here is that we can run the utilization script and see that actually the two nodes are actively participating in the training, and we see CPU utilization and memory utilization in both of the nodes. The training takes about 6 to 7 minutes for 10 epochs. And what we can see here is that the loss gradually decreases as the model becomes better and better through this training. To get a really accurate model, usually 10 epochs are not sufficient. And we need to train the model for longer. But for the purposes of this workshop, we'll just train up to 10 epochs. And while the training is finishing, I want to mention a couple of details. Usually in production, you would see distributed training happen on GPUs instead of CPUs, as we're demonstrating here, just for the purposes of the workshop. Also, the distributed file system would normally not be FS, but FSX for Lustre, which is a file system that provides much higher scalability and throughput, specifically for distributed training workloads. One caveat for FSX is that it only supports a single availability zone, which is important and usually the case when we're doing high performance training and want all of the nodes to be located as closely as possible together. So now the training is finished, and we are ready to execute the next step, which is to see how good our model actually is. For this, we will create a Kubernetes job which will run a pod, which will provide the model that we just created some new data that it has not used for the training, and we'll see how good the model classifies this new data into different categories. So let me scroll here to step 6, and we will execute the generate job script first to create this Kubernetes job manifest called Cypher10 test, which will also run on the C5-4X large instance. And it will use the same image that we have been using so far. And the command we're running inside the container is just Python, and then executing the Cypher10 model test script, passing the saved model and the location of the test data from the shared EFS volume. We're again mounting that EFS volume using the persistent volume claim the same way as we did for the training. So let's apply this manifest. We will see this new container, Cypher10 test, start running here immediately. And it completes pretty quickly because this is just an inference job for the model, not very resource intensive. And we can take a look at the logs that the test job printed out. So we've provided 10,000 images for testing to the model, and overall, it was able to classify these images with accuracy of 75%. And these are the various categories that it categorized the images in. It looks like this model is worst at being able to recognize cats for some reason, but it is actually best in being able to recognize trucks. So that is the test for our model. I want to point out that we have an extra step for cleanup if you wanted to decommission all of the infrastructure that we created so far. That is done in two steps. First, we would destroy the shared EFS file system. And secondly, we'll run an EKSCTL command to delete the cluster. We are not going to execute this step here, but that is how you would do it if you wanted to decommission the infrastructure. So I would like to go over these key takeaways from the workshop. First, we used AWS Elastic Kubernetes service to orchestrate and run a distributed training workload. We have 2 more workshops coming up that essentially do distributed model training using different services in AWS. One would be doing that on Amazon SageMaker, and the other would be doing that on AWS Parallel Cluster. Regardless of which orchestration mechanism you choose, the principles of distributed model training would be similar. For distributed model training, we use the PyTorch ML framework and Torch Elastic for Kubernetes. And finally, the architecture that we displayed in this workshop can be used for your own use cases, and you can access the code for it for an end-to-end description of all the steps, and you can borrow the source code from GitHub, which is available at this short link, bit.ly DTW-EKS. I want to take just one moment to say thank you to all of our collaborators who helped put together this content, especially the members of the frameworks team and our colleagues from Meta, Hamid Mazari and Matthias Rissel. Thank you for watching, and if there are any further questions, please feel free to reach out to us either on GitHub or LinkedIn. Have a great day.